Welcome to your first asynchronous lesson. Hope you enjoy it. So keep in mind on these lessons, you have the ability to watch whatever you don't get a couple times. So take advantage of that. Here we go. I am doing this last Wednesday. So it's before we did yesterday's lesson. So hopefully I'm starting in the right place. But it doesn't matter. If I'm repeating myself, that's not bad. So here we go. We're going to take this limit that we did yesterday numerically, and now we're going to evaluate it graphically. So to evaluate a limit graphically, that's exactly what you would think. You look at the graph. So it should give you the same limit, just in a different way. So to graph this, type in the function into y equals. So x divided by x minus 4. Now, as most of you already know, how I typed it in the calculator right here is not going to give me a good graph. The calculator will look at this as x divided by x minus 4, which will be 1 minus 4, which is negative 3. So if you look at the graph here, you have a line at negative 3, which is the correct graph, just the wrong function. I didn't type it in right. So make sure that when you're dealing with fractions, you use parentheses. Or you can always hit this alpha key down here, and then the y equals key, and it'll give you this little menu. The N over D key is very useful for those of you who always forget parentheses. So you type it as it looks. It creates a fraction for you, and this is exactly how that function looks on the screen. And now hit graph. So that's the graph of this function. Now the question is, what is the limit or the value of this function as x, the location, approaches 3? So the first thing we have to do on the graphing calculator is identify where x is 3, and that's obviously here. Now remember, if your graph doesn't look like this, it may be zoomed in or out. If you hit zoom 6, that's the standard zoom, and that's the one that you'll see all the 10 tick marks on every side. So here's 3. As you know, a limit will approach that x value from the left and the right. And if these values match, then that's the limit. So approaching 3 from the left, I drew this little dot here. I'm approaching from the left. So I'm following the graph, following, and I'm stopping right about here. About here. Now this is the problem with doing it graphically, is it's not that precise. So now we have to go from the right. So here's my dot on the right, and I'm approaching 3 from the right. It would be this graph. I'm off the chart here. Come back, start down here. Approaching. It hits it. They match at 3. It never got to 3. It shouldn't ever get to 3. Don't worry about what it actually is at 3. Just look at where those points are matching. And they match right about here. And the limit is a value, so it's a y value. The answer would be this. Now I'm getting the answer is about negative 3. Depending on how you read the calculator, you may be off a little bit. But according to this graph, this limit is negative 3 right here. So that's it. The next question, the next example, is this. That's a strange looking example that we probably looked at numerically. Let's look at it graphically. So graphically, we'll have to be able to type in the absolute value function. So let me just clear the top and bottom here. I'll throw the X on here. Now you have to find out where the absolute value key is. That's the math somewhere. What I like to do is, I know it's the first thing in the catalog. So I just do second catalog. And absolute comes up first and you hit enter. There's different ways of getting it. So that's what the function looks like. You hit the graph, looks like this. So now we're approaching 0. So from the left, take this point and I'll move it until I get almost to 0. Remember, you don't actually get there. So I'm almost at x equals 0 now, and obviously I'm at -1. Then you have to check from the right. So here's my point. I'm going to approach x equals 0 from the right, and I'm right here at 1. So from the left, I was at -1. From the right, I was at +1. These limits do not match. These values do not match. Therefore, the limit doesn't exist. The limit has to be the same constant number from the left and the right. So I can say D, N, E for this limit. It does not exist. One side note, one very important side note that I'll try to stress a lot. Might as well stress that now. Look at this function. Remember from algebra and trigonometry that this function has a vertical asymptote at x equals 4. And if I asked you why, you would probably say, because that's where the bottom equals 0. So if you look at this function, if I went from, by that definition, it has a vertical asymptote where the bottom equals 0, this function would have a vertical asymptote at x equals 0, and it doesn't. So remember, when you're looking for vertical asymptotes, those are going to be very important. Vertical asymptotes are where the bottom equals 0, but the top does not. So in this function, 4 made the bottom 0. It would make the top 4, so it does have a vertical asymptote. For this one, 0 makes the bottom 0, x equals 0, but it also makes the top 0. Therefore, this will not have a vertical asymptote. It will just have this discontinuous point that we will talk about a lot in the upcoming sections. Let's skip 3. So this one we'll do very quickly. Graph in the graphing calculator. 3x plus 1, 4x minus 20, and look very closely at the graph. So this limit is, we're approaching 5. X equals 5. So x equals 5 right here. 1, 2, 3, 4, 5. So I'm going to approach 5 from the left. And you can see that it's going to go down and down and down and down and down to negative infinity over here. That's enough to tell you the limit does not exist, because the limit has to equal a constant number. Infinity is not a constant number. But I'm going to go from the other side as well. From the right, it's going to positive infinity. So not only does it not approach a common number, but those infinities don't match. But that doesn't matter, because if you get positive infinity on both sides, it still does not exist because it doesn't approach a constant number. So we will say D and E on this. Now, one more thing. I just talked about vertical asymptotes. It's obvious that 5 makes the bottom 0. If you plug 5 into the top, it makes it 16, which is not 0, which means vertical asymptote. Okay, so here's a great example of that. You see question number 5. It's very close to I mean, not very close. It's a limit as x approaches 5. The denominators are the same, but the numerators are not. So before I do this, think about what we said about vertical asymptotes. And now look at the function. So let's see what happens. I'm going to graph that function, but this time it's x minus 5 up here, so delete. And then I'm going to hit graph. That's weird. So we're going to discuss two quick things here. Number one, there's obviously not a vertical asymptote, because a vertical asymptote means a function increases without bound or decreases without bound. Number two, it just looks like I guess a straight line. What I would do here is let's zoom in towards 5 because it's hard to see. So I'm going to go to my calculator and hit zoom, 2 for n, and now I'm going to, before I hit enter again, I'm going to scroll over until I get to about x equals 5, which is right here. Hit enter, and there it is. So the limit, as you go to 5 from the left, stop here, it's this value. As you go to 5 from the right, it's this value. Those are constant numbers, constant values, they match. So this does have a limit. It's whatever that value is. I'm assuming this is 1 here. So I don't know. That's the problem with graphical limits. Let's guess 1/4, 0.25. And we're going to have to live with that, I guess. You can check that numerically too. Just plug in 4.99 and 5.01. One more, or two more things, I guess. The graphing calculator is not capable of graphing this correctly. Everything's correct about this graph except 1 point. And this is going to be, again, a very, very important point here in this chapter. At 5. If you plug in 5 to the bottom, we know it's undefined. Therefore, this function is undefined at 5. There should not be a part of the graph that goes through 5. So what it really looks like here is at 5, it has an open circle. But again, that's a good point for limits. The limit still exists because the limit never actually gets to the value. It just approaches it. So the limit doesn't even know there's an open circle there because it will never get to 5. It just thinks it's 1/4 on both sides. So before I end this video, I want to show you one more thing. And maybe some of you have figured this out already. Maybe if you've paused this video, which would be a good thing to do while you're watching these, you looked at this function more deeply. But the function x minus 5 over 4x minus 20 can be factored and simplified. So this does equal 1/4 everywhere. So 1/4 would be the same limit. But one very, very, very important thing about what I did here is see this equal sign? This is equal to this function. See this equal sign? Not really. This does not equal 1/4 because 1/4 is defined everywhere. This function is not defined at x equals 5. So if I want to include that equal sign mathematically, I would have to say this function equals 1/4 for all x except x not equal to 5. And that explains the open hole. We'll talk about that in more detail as we go. So I'm going to end this video here. I'm going to follow it with a very short video, maybe not very short. I tend to go on, but that's it for now.